All right, 4.5. 21. We're supposed to find the number of zeros, positive or negative, based on Descartes' rule. Descartes says if these are in order, 7, there's no x to the 6 or 5 or 4, x to the third, x to the second, no x to the first, and x to the 0. If these are in order, the number of sign changes in this, so this goes from positive to negative, negative to positive, positive to negative, negative to positive. So there's a change from negative to positive, 1 change. From positive to negative, 2 changes. From negative to positive, 3 changes. It says that there's 3, or they go down by 2, 3 or 1, or negative 1 couldn't be. So there's 3 or 1 positive zeros. And then for the negative, you decide which of these terms would change sign if x was a negative number. Well, a negative to the 7th would be a negative, and so that would change this to a positive. A negative to the 3rd would change sign, so that would be negative. A negative to the 2nd wouldn't change, so that stays negative. And this is a +2 because there's no x. So we have a positive to negative, 1 change. Negative to negative, not a change. Negative to positive, that is a change. So there's 2 going down by 2, or no negative zeros. And that's what Descartes' rule says about sign changes in the coefficients. So if we go to 30, we'll do the same kind of thing. For the positive, let's see. Positive to negative, 1 change. Negative to positive, 2 changes. Positive to negative, negative to positive. Positive to negative, 3 changes. Negative to positive, 4 changes. Positive to negative, 5 changes. So there's 5. Or, down by 2, 3 or 1 positive zeros. And now we'll go back through, and all the odd-powered terms will change their sign, because a negative in here, this would go to a negative. This would stay negative. This would go to negative. This would stay negative. This would go to negative, and this would stay negative. There are no sign changes, so there are 0 negative zeros. All of them are positive. Again, this whole thing with Descartes' rule of signs is for when they didn't have a calculator to kind of look and see where they are at. So this would help them when they take the possible rational roots and check, and they would know in this particular case you wouldn't have to check any negatives because it's not going to work. Okay, 50. So if we were just to do the Descartes rule, there's no change. There's only 1 change. So there's 1 positive root. And we could be factors of 30 over the factors of 3. But from what I touch in class, we can just type this into y equals. Clear this. We got 3x to the 3rd plus 6x squared minus 15x minus 30. We can graph, and we should see that there's 1 positive root and some negative roots here, and the positive one is not real clear here, and the negative one looks like it might be -2. So let's go zoom 4. That'll be a little closer in. Let's take a closer look. Oh, it's not 2. It's not there. Let's make sure I've got this in right. 3x to the 3rd plus 6x squared. I better check with the problem in the book too. 3x to the 3rd plus 6x squared minus 15x minus 30. So go back to the graph. Hopefully, oh, maybe that one there at -2 isn't exact. So I'm going to check that. Second, calculate the value at -2. Let's see if it comes out. Yeah, -2 is a nice one. So I'm going to use that in my synthetic division. I'm going to write, I have 3x to the third, 6x squared minus 15x to the 1 minus 30x to the 0, and I'm going to try -2, which would mean x plus 2 is a factor, and I get 3, -6, 0, 0, -15 times -2 is +30, 0. And I'm left with 3x squared minus 15. And I can put that into the quadratic formula, but I can also, if I'm trying to get this to be equal to 0, I can add 15 and divide by 3, and I get x squared equals 5, and x equals plus or minus the square root of 5. That's the other two zeros. So this factors to x plus 2, x plus the square root of 5, and x minus the square root of 5. And that's that function factor. Okay, now we'll go to 57. 57, it says solve this. Well, again, I could use the rational root theorem that there's got to be factors of 8 over factors of 1. So it's 4, 2, or 1, positive or negative. How many are positive? Let's see. 1 sign change, 2, 3 sign changes. So there's 3 or 1 positive roots. And if I change that to the negatives, the odds to change their signs of those, that would be positive, 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 negative. There'd be 1 negative. And there's 4 total, so, and if there's, so it could be 3 and 1, or 1 and 1, and 2 imaginary. So let's kind of take a look at the graph to get us started here. So clear x to the 4th minus x to the 3rd plus 2x squared minus 4x, subtract 8, graph. Looks like -1 and +2. So we'll go to synthetic division. 1, -1, 2, -4, -8. Try -1. Looks like that's our 1 negative root. -1, 1, -1, -2, 2, 4, -4, -8, 8, 0. So that worked. Now I've gone from a quartic to a cubic, and I think +2 happens once, so I'm going to put 2. 1, 2, 0, 0, 4, 2 is 8, 0. So that worked. And I'm left with 1x squared plus 4. And if I'm trying to make that equal to 0, I can subtract 4 and take the square root. And x would equal plus or minus the square root of -4. Square root of negative is I, and square root of 4 is 2. So my solutions are, it says to solve, so x can equal -1, 2, 2i, and -2i. And finally, 77 says find the bounds on the zeros. So let's find the positive bound, which, let's see, we got minus 1, 3, negative 4, minus 2, 9. The signs change, so I've not reached the upper bound. So I'm going to start moving up, and it has to be factors of 9 or factors of 1. So it could be 1 over 1. So I'll put 1. Minus 1 times 1 is minus 1. This is plus 2. The signs change, not the upper bound. So I'll go to 3. Minus 1. 3 times minus 1 is minus 3. That's 0. Zeros could be considered minus, so that's not a sign change. 3 times 0 is 0. Minus 4. That's still minus. No sign change. This is minus 12. That'd be minus 14. That would be negative 42. So negative 33. No sign changes. Zeros doesn't count. So therefore at 3, and I have a 0 in it, that means we're right at the edge. 3 is the upper bound. That's how high I have to go to get no sign changes. Now I go down until I find every time it changes sign. So I'm going to start over again with the minus 1, 3, negative 4, negative 2, 9, and I want the signs to always change. So I'm going to start down. I could try with a minus 1 first and work my way down. So minus 1, this would be minus 1, this would be 1, that's positive 4, that's a sign change. This would be minus 4, that would be minus 8, that's a sign change. Minus 1 times that is 8, that's positive 6, that's a sign change. Minus 1 times that is minus 6, and that's 3. That's not a sign change. So minus 1 is not quite the lower bound. The next number I would try would be, again, a factor of 9 over that, which would be negative 3. So not into this, into the original. Sorry. So I got to think up here. Minus 1 comes down. Minus 3 times minus 1 is 3, so this is 6. Minus 18 and minus 4 is minus 22. That would be positive 66. This would be 64. That would be minus 192. And minus 192 and 9 is negative, and so minus 3 would be a lower bound. It might even be minus 2. We could try minus 2 because this was pretty close to doing it. I'm going to guess minus 2 does. Maybe I should try that. Let's see here. Let me slide this down here, get a little more paper. I'll do it on this one. White waste paper. So I've got minus 1, the original function at minus 1, 3, minus 4, minus 2, 9. If I do negative 2 might be the lower bound. Minus 1, 2, 5, negative 10, negative 14, 28, 26, negative 52, and so this is negative, and so everyone's a sign change, so negative 2 is actually a better lower bound. And what I could do is keep coming back towards minus 1 until I found out where it's 0, but they usually are looking for the bounds in integers. So I did minus 1, it wasn't. Minus 3, it was by a lot, and so then I did minus 2, and it's still by a fair amount, but closer to being just enough. So that's the one I went with. Okay.